Hi and welcome to another lesson in the subroutines series. Today's topic is the stack. Objectives of this lesson. We will learn about the stack data structure. We will study the x86 stack implementation and instructions. Finally, we will see some examples of using the stack. Let's begin with the idea of the stack. The stack is an abstract idea for storing data. Only two operations are allowed, push and pop. The last element pushed into the stack is the first element to be popped out of the stack, which corresponds to the LIFO principle, last in, first out. Let's see an actual example. Let's assume that this is an empty stack. We push one element into the stack, the green one. Then we push another element into the stack. And finally, the third element is pushed into the stack. Now note that when we are going to pop an element from the stack, the element which is going to be popped is the last one which was pushed into the stack. So now when we are going to pop an element from the stack, it is going to be the red element, which was the last one pushed into the stack. The operation of taking elements out of the stack is called popping or pop. This is basically a stack. To make sure that you remember the concept of a stack, let's take a look at a few real-world examples. A stack of pancakes, a stack of CDs, a stack of books, and a stack of chairs. The ESP register. At this point, I want to talk a bit about the implementation of the stack in the x86 architecture. ESP is a 32 bits register, also known as the extended stack pointer. It is of size 4 bytes, which are 32 bits, and its lower part, the lowest 2 bytes or 16 bits, is called SP. Originally, in the first x86 architectures, there was only the SP register. ESP came later as an extension of the SP register. At the moment your code begins to run, and I talk about the programs that you write, ESP already contains an address of a location in memory called the stack. Both ESP and the stack are set up automatically by the operation system, which means that you don't have to do anything special. In the beginning of your program, you already have the stack and ESP pointing to some location inside the stack. This is just an illustration of how it probably looks like. I want to note that the location which is called the stack in the memory is just a part of the memory. Nothing is really special about it. There are some special instructions that deal with ESP and the stack. They allow us to manage the stack and change the values of ESP and the stack's contents. The first such instruction is push, which corresponds to the push operation on the stack. It stands for push onto the stack, and it has two forms. The first one is the 16-bit form. The push instruction gets exactly one argument. If this argument is of size 16 bits, then we are on the 16-bit form. In this form, ESP is decreased by 2, which corresponds to 16 bits, because 2 bytes are exactly 16 bits. And then we store arg into the word pointed by ESP. Note that we first subtract and only then we store into the address of ESP. The order matters here. The second form, which is really the most common form, is the 32-bit form. In this form, we first subtract 4 from ESP, and then we store arg into the location ESP in memory. In this form, arg has to be of size 32 bits. It is most likely that you will never use the first form, mostly because of alignment issues. If you push a value of size 16 bits to the stack, it means that all the other elements of the stack, which will follow this 16-bit element, will probably not be aligned to have addresses divisible by 32 bits, which means that your program will be a bit slower. Therefore, you will usually use this form. You don't have to remember the reason for using this form, but you should remember that this form is the one that you should use. This is mostly because of efficiency reasons, and most of the time it is going to be more comfortable to use the second form, because we are working in 32 bits protected mode, and most of the values that we are going to encounter are going to be of size 32 bits, especially addresses. Let's take a look at a simple example of using the push instruction. Here we can see two different types of the push instruction. In the first type, we push an immediate into the stack, and in the second form, we push a register into the stack. By the way, you can also push the contents of a memory location into the stack. So let's see what happens. Assume that this is the stack, and the addresses increase to this direction, as usual. Also assume that ESP points to this location in memory. So first we push this value, 1, 2, 3, 4, 5, 6, 7, 8 in base 16. The result is as follows. Next we move 3 into EAX, which is going to store the value 3 into the register EAX. And then we push EAX, which is the equivalent of pushing the number 3 into the stack, which is going to result in the following picture. The next instruction, as expected, is called pop, and it has the form pop arg. In this instruction, as opposed to the push instruction, arg has to be some kind of container, because the result of the pop is going to be inside arg, is going to be stored inside arg. Pop basically stands for pop a value from the stack, and this value is going to be stored inside arg. Pop has two forms, just like push. It has the 16-bit form, where we first read a word from the location ESP in memory into arg, and then we increase ESP by 2. The other form is the 32 bits form, where we read a D word from the location ESP in memory into arg, followed by increasing ESP by 4. Again, we are mostly going to use the second form of the 32 bits, of the same reasons for the push instruction. I want to note another important difference between push and pop. Note that in the pop instruction, we have this order of operations. We first read from memory, and only then we increase ESP. However, in the push instruction, we first subtract from ESP, and only then we store into the location pointed by ESP. So push and pop are somehow dual instructions. They complement each other. Let's take a look at a quick example of using the pop instruction. We continue from the previous example. Assume that this is what we currently have inside the stack. You probably remember those values. This is the 1, 2, 3, 4, 5, 6, 7, 8, and this is the 3. Currently, ESP points to this location. We begin by popping into EAX, which means that the current value pointed by ESP inside the stack is going to be stored inside EAX. And as expected, we get that EAX gets the value 3. Next, we pop into ECX, which means that this value here is going to be stored inside ECX. And as expected, we get this value inside ECX. Let's look at an example of exchanging values. We are going to exchange two values. In this example, we want to exchange the value of EAX and ECX. We want the values to switch. We could do it in some other ways. For example, we could do it with an intermediate register. But I just want to show an important example of using the stack. Using the stack, we can do it this way. Let's try to follow this example and understand what really happens. Let's begin with following this code. We will go instruction by instruction. We assume that EAX initially contains this value, 1 till 8 in base 16, and ECX contains this value. And we want to exchange those two values, which means that in the end of this process, we want that this value will be inside EAX and this value will be inside ECX. This is a picture of the stack in memory, and we assume that the addresses increase to the right. We also assume that ESP points to this location. So let's begin. We first push EAX into the stack. Next, we push ECX into the stack. I want to emphasize the change that happened in ESP. So let's take a look again. ESP begins with this value. It then decreases by 4. And then again it decreases by 4. Note that when we pop, this value is going to increase. As we pop downwards, it will increase by 4. Let's follow what happens now. We pop into EAX, which means that this value is going to be popped into EAX. And indeed, we get that EAX now has this value. Finally, we pop from the stack into ECX, which means that now ECX contains the value 1, 2, 3, 4, 5, 6, 7, 8. And as wanted, we managed to switch the values of EAX and ECX. Recall that EAX originally contained this value, 1 till 8, and ECX contains this value, AA, BB, CC, DD. Let's take a look at another example, which is pretty important. This example is about saving and restoring. We want to keep the ECX register unchanged. This is a pretty simple example, but it could be a much more complicated piece of code. We basically assume that we have this push and pop. Push in the beginning and pop in the end. And in the middle we have some calculation that changes ECX. And we want to make sure that the initial value that ECX contained will be the same in the end, after this pop instruction. Basically, we just keep ECX before we begin the calculation, and then in the end of the calculation we restore ECX to its original value. Let's take a look at the code to understand what really happened. This one is pretty simple, but I just want to make sure that we understand how it works. Again, we have the stack on memory, and we assume that the address has increased to the right. We also assume that ECX initially has this interesting value, and ESP initially points to this location, which is this address. First, we push ECX to the stack, and this is what we get. We get this number inside the stack, which is what was originally inside ECX. Next, we do the calculation, which here is a pretty simple calculation. We just increase ECX by 1. But it could be something more complicated. Maybe, for example, we used ECX for a loop as an iterator, or maybe even something more complicated. Now we increase ECX, so we get this new value for ECX, and now we assume that we finished the calculation and we want to restore ECX to its original value. So we pop from the stack into ECX, and we get the original value. So now we have a method to keep the ECX register unchanged. If we wanted, we could extend this method, and we could maybe keep more registers unchanged. It could be done, for example, this way. For example, if we have some code that changes many registers, and we want to keep ECX, EAX, and EBX unchanged, we could use this form of code. It is easy to understand that ECX is unchanged, because you can just think about all this code beginning from push EAX until pop EAX as the code that we had in the previous example, which is here. So obviously ECX is left unchanged. You can next think about the push EAX and pop EAX, which ensure that EAX is kept unchanged. And finally, those two instructions, push EBX and pop EBX, ensure that EBX is left unchanged. Note the push and pop order. This is pretty important. If we used some other order, it wouldn't work. Maybe if we switched here EBX and EAX, we will get as a result that the original value of EAX and EBX will be swapped. They will be exchanged somehow. So if we want to keep the same values from the beginning in the end of the code, we have to use this order. In the beginning we have the order ECX, EAX, EBX, and in the end we have the reversed order, EBX, EAX, ECX. This is a very important code idiom when programming in the assembly language, so make sure to remember it. Summary of this lesson. A stack is an abstract idea for storing data. It supports basically only two operations, push and pop. Push adds an element to the stack, and pop removes an element from the stack. It follows the concept of last in, first out, which means that the last element pushed into the stack is the first element popped out of the stack. I want to note that the idea of the stack is an abstract idea. It is not bound to the x86 architecture. It existed much before the x86 architecture, and it will also exist after the x86 architecture. We have learned a bit about the x86 stack. In the x86 architecture, the ESP register always points to the top of the stack, which means that it always points to the last element of the stack, the element on the top, the last element that was pushed into the stack. We have also seen the push and pop instructions. The push instruction decreases ESP, and then writes to the stack, as opposed to the pop instruction, which first reads from the top of the stack and then increases ESP. This is a picture that could help you remember what happens during push and pop. We've also seen two important examples. The first one was about exchanging values using the stack, and the second one was about saving and restoring values. See you next time.